So we just not start yet, but in case you are free, I just let you know that I just add some slide to the Blackboard one. So I mean, there's nothing new, but I just add more example there. So if you might or may not use the new one, but otherwise there's no particular difference compared to the one that I just add some example that might be useful to understand, but there's nothing changes in the. You can still use the existing one. So I guess we can start. So I think you have a nice non-weekend, and we lose Monday, and we will probably lose another Monday, right? Because of the Chongyang Festival as well. And I probably mentioned as well is actually the Monday also the week after next Monday, I also have to cancel the class because of I have some other obligation to have fulfilled. But anyway, we already have the 2 3 hours Python class on the Chongyang Festival. You can join either, or you can just Zoom, or you can just you don't have to go to or you can look at the record. That's fine, optional. And possibly after that, I will see how it goes. Depends on whether the next one will be another section of Python or actually go to R. So, but of course, both Python R will be optional. So it's not in the exam, not in the assignment, but I think it's good for you because these days, how to control that would be useful. Okay, and so today we will talk about the random variable. Okay, I will make the announcement on the Blackboard about the makeup class and some the cancel class. Okay, but I make sure that the makeup class will be there, so don't worry. And so let us very briefly review what we have done. Okay, so in topic 1 we talk about summary statistics, mean and variance idea, and topic 2 we talk about probability, right? And now topic 3 is called random variable, which is basically you can say if you study a introductory stat class, we'll stop here. Okay, because you will see these topics already a lot of application there. Okay, and then later you see the example, and I have mentioned that I add some slides to the one that I just updated last night, and because of I taught the other section in yesterday, and then they seems to be the case is I make it too brief, so I add more example there, but shouldn't change anything. So just to remind you what is random variable, in business sense, it's like you try to look at some quantitative variables, right, to present uncertainty, right? The random experiment, the outcomes are not number, right? But all the time you care about quantitative measure, right? Like the stock price, right? Stock index performance, right? How many profit you're making, right? And this is something you care, right? Suppose you are the restaurant owner. You don't care about the next customer is a boy or girl, where he wear t-shirt or where he have dress or skirt, whatever. We care about how much money he spent or she spent on your restaurant, right? Just summarize the number, right? And the random variable will serve that purpose. And what kind of random variable we're looking at is very important because the support, and that actually the importance is on a more technical idea about discrete or continuous, which is the idea behind the math, because the discrete is the thing that you can easily use the tools that you learn in the high school to do it. But for continuous, you actually involve infinity, so you really require calculus. But everything actually discrete will carry forward to continuous. So if you have time, we'll touch a little bit today to explain the difference. Just to remind you that discrete, you can count it, so it's just like integer, right? Just to remind the example is we have toss a coin, is head or tail, the outcome. But instead of head and tail, we count the number of heads. It's 0 or 1. This is a number. So we're able to change the number, and things become easier to describe, right? Just like the random variable is telling us how each outcome from the sample space map to numbers, right? And what kind of number can be here? If it's integer, then it's like discrete, right? If not integer, then decimal numbers, then become a continuous, right? So this is a total coin twice. If you just care about number of head, okay, then that is a quantitative measure, which is also meaningful, right? You just don't care about the order appearance, right? HT and TH are the same, right? And this is going to be this, and then we know actually this is a binomial distribution later when we see, okay? And this is the thing. And as I mentioned, you can assign any number to that, right? But that is not very meaningful unless you have some idea. So continuous is the thing that about money or the stock or profit or numbers, right? Decimal numbers. This is the thing that we usually do for business. It's most natural to see this, right? You care about money, right? But if you do counting number of people, number of accidents, then still discrete is the way to go. Okay. So because we know discrete very well, right? Because this is what we do in the primary school or high school. So that's why we introduce how to handle random variable in discrete case. Everything we learn actually carry to continuous. Okay. So about expectation and variance, everything apply to continuous. But let's talk about discrete. That makes life easier. Okay. And now the uncertainty about the future is measured by random variable, right? We just say what is going on is just a number, right? Just I don't know today's temperature, right? Today's weather, or how many customers coming, right? And the random variable big X equal to a value small x, right? And it's called probably mass function. The mass will make sense if you learn physics later. You will see when we have a continuous random variable, this becomes the probability density function. If you learn physics, you know what does that mean. But we'll try to explain that to you. And some other book they use PF or PDF, but some of the book use PMF. But we avoid the shortcut form. We just call the big P, okay, in our class. And this is example, right? Just to recall, if you toss a coin, right? It's a fair coin. Number of head is either 0 or 1, okay? And you can, from that, right? Because head is mapped to 1, tail is mapped to 0. Then you can have a big P, right? By this construction. Is that okay? I think I slightly change the slide so that it become easier. I hope this become an easier one. And this is the cumulative function or CDF or distribution function, which is saying that come from P, okay, it's just stacking the P up, right? It's the bar graph. You're just adding everything less than or equal to that value, right? So if you look at the table from the P, right? F will be just adding up the number above and on the left, right? So this is just this guy, there's nothing left, is this guy. This guy I get is just go up and go left, right? Adding everything there. It's the definition of big F, right? So I write down in here to elaborate more. So some of you may see the difference between the slides and what you have is just nothing new, but I just add things there. Okay. So if you have using the older version, then it doesn't really matter anyway. Okay. If you understand, then it's there. So there's nothing particularly new in this slide. Okay. So and this is a graphical representation, right? You have the red and the blue one, the P, and then stack them up, right? That become the F, right? That's how you see it. So remember this, we will carry this idea from discrete to continuous, okay? Stacking things. And as you see, this is why you have integration here. But because of you're stacking the area on the left, it's just integration. But it will be more clear when we talk about continuous later today. Here I just give the same thing. I just give more steps and how I derive the second row, right? Or the first row, right? The first row is you toss a coin 2 times, right? And that would be you have head, tail, head, and tail, right? You count the number of head, right? And the 4 outcome are equally likely, right? So P0 we just refer to TT, just 1/4, and x equal to 1 will be XT and TH, right? So that is going to 1/2, right? And x equal to 2, right? X equal to 2, right? And this is going to be only 1 for x is 1/4, right? And F is simply, remember F is simply you go up what the number is and go add everything on the left hand side. So this is just 1/4. This Y you just go up and add everything there, right? Because definition, right? This one you go up, add everything there is 1. So that's how I get this, right? Or the same as you're stacking the bar graph, right? So you just here just this guy, right? This guy you just stack, right? And this guy just stack and stack, right? This definition, right? Is that okay? How you get from left to right? I hope it's clear at how you get that one. And that means that this graph tells you you can always describe a random variable by big P or big F is equivalent. Okay, you can come from here to here, right? You subtract this to this, give you this guy, right? Subtract this to this, give you this guy. Subtract this to this, give you this guy, right? So that's a equivalent way to describe a discrete random variable is either through P or through F. Okay. So this is usually when you listen to the people how they describe the probability, right, of a random variable. Okay. And this one is another way to write, right? Tossing a roll a die. So I guess that shouldn't be an issue, right? The only issue I don't remind those QFN students or students who want to do further studies is the way we write the bar graph is not precise, although it's implicit implied. Actually, the number is not included with 0, right? Because roll a die, the probability getting 1.5 is 0, right? Because roll a die is only 6 outcome, right? So you have all these things, but since we're not technical class, we are not need to be that precise. But in case you try to study further, then you may see this issue here. Same for the CDF, right? Although we write in the bar graph in this manner, but if you to be careful, it is actually a step function, but it's not required for our class. Just in case you read some advanced textbook, you will notice the way we do, and by definition, is technically it's left continuous, but the right continuous. But you put the dot here because it's less than or equal to, so that's why it jumped in this one, but not here. But anyway, not a big deal. And what we cover is the random variable, right? How does it connect to topic 1? Actually, is the expectation and variance is a connection between topic 1 and topic 2, right? And the mean and variance. So if you have random variable, right, a number, right, and then if we run this experiment many times, and every time we got a lot of numbers, right, and we want to look at what is the average value, mean of the value, right, of the number, and turn out this is exactly the expectation means, right, is the weighted average or the average of this stuff, right? We keep this experiment many times, and each time we record a number, average of those number, right, with this one, and in that case, it's just simply the value times the probability add up, right? And I explained the reason why this is true is you consider the case you toss a coin 1 million times, right? If a fair coin, you expect to have 500,000 head, 500,000 tail, right? Because random variable is number of head, so we have 500,000 0, 500,000 1, right? And then 500,000 over a million, that turn out to be 0.5, right? So this is exactly same as 0 times probability of 0 and 1 times 1. Okay, so that is exactly the minimum of expectation. Okay, and this is how you calculate expected value, right? 0 times 1/2 plus 1 times 1/2. So this is you expect the value, right, is 0.5, right? So do remember this idea is supposed to run this is average of that. Okay, it's not saying that you have a 0.5 tail, right? Because there's only one tail, one head or no head, right? So, but we're saying that if you have many times, it's you have it's close to half of that. Okay. The same idea, you roll a die, right? Average value will be 3.5. Okay, and we give some property of calculating variance, the expectation, and remember how to figuratively understand this formula is you can imagine X is the return of the stock, and then the last line which encompass the first two lines is saying that if you invest A quantity of stock X plus B in the bank as a cash deposit, okay, with 0 interest, okay, and what is your expectation of portfolio will be, because you buy A of stock X, so it will be A times the expected return of stock plus the cash. Okay, so so that would be the thing. And why it's important? Because we don't need to think of a whole portfolio. We can divide and conquer. We only need to think about the return of a particular stock, not a return of 1 stock, 2 stock, 3 stock, 4 stock. If not linear, then our life will be very difficult, right? Because we have to think about what happens if you invest 1 stock, what happens if you invest 2 stock, 3 stock, and 4 stock, then it's much more difficult. So our life is easier in that sense. And variance, the same idea, right? Because if you remember, variance is from topic 1 is what we call the square distance from the mean, right? You look at the mean, each number minus the mean and take square and add up all the observation over n. The same idea is expected value, the square distance, the distance from the mean you square, right? So it is this guy, okay? It's denoted by sigma square, and this is usually how we do the calculation. There's nothing new, right? Just take each observation, the 1 minus the mean, and raise to the power square, and times probability. You do this for the rest, right? And some of you ask, okay, if you do assignment, do you need to write down all? Probably just write the first, the second, and last. You can write ... Then you come the answer. It's the way to demonstrate, you know. Okay. And for the variance, just the same idea. Remember, you invest X amount of stock X plus cash. And the good thing is if cash is a constant, has no variation, it has no contribution to the variance of portfolio, right? And you have invest A quantity, then the variance actually become A squared bigger, okay? And if you take the square root, which gives you standard deviation, right? And then you can see the standard deviation just 8 times larger, okay? It's not 8 times square bigger. So that is the thing that's why standard deviation is more natural, right? Because if you invest 100 stocks, right, the standard deviation is just 100 times of the individual stock, right? So that is, but if you are talking about variance, right, then will be 100 square. So it's your mind twists a little bit. So don't be easy for you, but you have to think, right? And here we have something we omitted for those QFN student or student who want to do step further. This part is very important because the foundation of this is you want to talk about multiple random variable. There are 2 random variable to represent the sample space, right? Because instead of using 1, you have 2, okay? Because you can imagine that I talk about finance, right? The stock market has more than 1 stock, right? Of course, you can say the stock index, that's something you care, but if you want to talk about which individual stock you want to buy, how much you want to buy, the portfolio theory will require you to understand the stock market as more than 1 random variable, okay? And the way we do is we have to define what we call the joint probability function, and that is way more complicated than we can cover in our elementary class. If you want more, the 2021 will cover the 2021 to cover the foundation for that. And if you do more, they'll cover more. So it's way beyond our class, okay, to cover that. But we will just assume that we know how to handle more than one random variable, okay? And the way we focus on is we call the independent, okay? So we consider 2 random variables that are independent, so we can treat them separately, okay? So, but this expectation of the sum of the random variable actually don't need independence, okay? It holds for random variable in general, okay? In all the cases, it just, if you invest stock X and stock Y, you buy A of X and B of Y, you just can separate them, right? You just calculate the stock return for each stock. It's just times A and B respectively, then you're done, okay? So you don't, if you look in the stock return, right, you just focus on each individual stock is sufficient, okay? That makes our life easier to calculate. And variance of your portfolio, right? The same idea is you don't have to worry too much about the variance. If they're independent, you just add them up, right? Basically, sum of the variance of the sum is sum of the variance, okay? If they're independent, and we'll rely this fact to work on sampling in the next topic. So this is a formula that we have been using. Well, we will use, I think after next week, okay? And this is a covariance. And one thing that we actually omitted, and you probably will study a lot when you do investment class, is about covariance, right? Because if the 2 random variables are unrelated, right, means that they're independent, right, the covariance will be 0, and you can think about investment investing them separately, right? But now, because the variance add up, right? But now very often the stocks are related, right? And that means that covariance, actually the same idea what we learned in the topic 1, right? One goes up and one goes down, right? They go down the same direction or different direction. And in those cases, right, the variance sum will be covariance plus, variance plus the covariance term. This extra term there, right? If they're independent, you don't have this. Now they're not. That means that if you are an investor, which usually they're risk averse, right? And variance is measure of risk in finance theory, right? That means that you want to make this as small as possible. And these two, you can't do anything. The thing you can do is figure out the one that make this small, right? So that actually you want to reduce this covariance is diversification, right? Remember the old wisdom, don't put all the eggs in the same basket. Why? If you put the same basket, the covariance, you can realize right, the covariance is 1, right? Because either it breaks, everything breaks, right? If you put the basket here, put the basket there, when one big, the other one doesn't, right? Or unlikely they are big, of course, an earthquake, the everything breaks. But you put there, then safer, right? So that's why the covariance gets smaller, right? So that's why people try to do diversification. People look for alternate investment. People look at the hedge fund, look at some angel fund, seed fund, whatever, is trying to reduce this, right? And people invest in gold. People do the cryptocurrency, right? These are the idea, or antiques, invest in wine or Rolex watch. The reason is diversification to reduce covariance. And that's the reason why you see recently the JPEGs, I think called JPEG, I don't know how to pronounce it, JPEX, JPEGs, right? JPEGs, right? The reason why so many people invest so much money on possibly a scam or cryptocurrency is not because they are all stupid, right? Unlikely, but very likely because they figure out the covariance is very high in the recent case in Hong Kong investment, right? So if you invest in stock, you know the stock market is not doing very well, and stock market is mainly in Hong Kong. Is most of them are Chinese company, right? So it's a lot of correlation there is because a lot of Chinese company and they don't have much diversification. The stock is also related. That's why, and the housing market is also closely related with the stock market in Hong Kong. So that's why you don't have much opportunity, right? So that's why these days you see a lot of people go to cryptocurrency or go to invest in the US stock market because try to make this as small as possible, right? And also many of people in Hong Kong actually have the retirement fund, the M.Phil, right? It's also a lot of them invest in Asia area, right? So you really want to diversify somehow, right? So that is the reason, but you will learn how to diversify in the investment class. I think if it's still the same cost code is FINA 3080, I think, 380, something like that. You spend the whole semester to understand covariance structure and so on and so forth. Okay, and that is something that Nobel Prize, right? The Markowitz portfolio theory. But it's not our. You spend the whole semester to learn those. But if you want to, here is I guess we spend 1 month to learn so much stuff, right? This is one of the milestone we want to learn is how to use probability statistics to apply in the practice. Okay, because remember the probability is to model uncertainty, model the future, model business situation where haven't realized, right? And then we want to make decision, right? It's modeling the future. How to model the future is probability, right? And we talk about random variable is to measure of some outcomes, right? And here is we introduce several common distribution, okay, or some description of random variable, and which is you will find a lot of application in practice. And we'll give a more example on this, okay? And then you will see how what we learn for 1 month, how it's useful, okay? And the data that we obtain in the real world will help us to build this model, and that will fit to our application, okay? So the idea is we have some data, right? And data tell us how this mathematical model works, and this mathematical model will help us to do actual business decision. I will give more example, and because yesterday I taught this and they think that I need more example, okay? So you will see more example compared to the slide you have maybe, but this is slide already in the okay. So this one we have been using all the time. It's called the uniform distribution. Is every outcome is equally likely, and this is just like rolling a die, right? Die is a 6 outcome, 1 to 6 is equally likely. And probably you ask how often we use this. Actually, this is something that if you don't know what's going on, uniform is a good starting point, okay? And probably you ask, okay, what's next? That is the base theorem tells you, you update, you have a model from uniform, you update using base theorem, you keep learning, okay? That's actually what AI is doing, right? AI actually trained it a lot of time. They keep training the probability model and train, right? If you look at what the ChatGPT doing or the Bean, whatever they think is a probability model, right? Just like it's a text, right? They get based on what you have, what's the highest probability thing that would make sense. Then that's how they generate outcomes, right? There's a base theorem there, right? Keep updating. Given this first output, update and update, keep doing. It's base theorem, it's base theorem idea. Okay? But uniform is the starting point. Usually, this is the thing you would be doing. Okay. And now we go to this useful one. The base building block of this one is called the binomial distribution. And this is the most basic one. It's either success or failure. Okay. And actually, yesterday, some of the students asked me, okay, when I have more than one outcome, which sometimes you don't want to just say success or failure, you want something like high, medium, low. It's doable, but it's beyond the scope. It's called multinomial distribution, but it's not we can do a trinomial distribution. That's fine, okay? But it's not something that covered in the class. We just do success or failure, and then the probability is P and 1 minus P, okay? And X is number of success, okay? So by construction, this is very simple. The P function is just this guy, right? This is the description, right? So whenever the model is the simplest one you can imagine, right? You just have success and failure, right? For the future, I can define this common P and 1 minus P, okay? And probably one of you may ask, how do we get this P? From the data, okay? Let's learn from data to tell us that's what it is, okay? And how to get data, that actually is rely on the fact that look at the mean and variance, right? Because of if binomial, this is the mean and variance, and look at data, you can calculate mean and variance, you're trying to equalize them, okay? And this is what we call method of moment. It's not covered in our class. I think it's covered in very advanced, maybe 3,000 or 4,000 classes. That's how we map the data, okay? In our class, we just give you the number, okay? But in the real world, if you want to estimate those, actually there's some way to do it, okay? There's several ways to do that, but the easiest is look at the data, what's the mean, and then you're done. Match the P, that's called the, this is the method moment, okay? But this is the form is exactly same as that table, right? The most simplest one, okay? And just to remind you, the variance will be the smallest when the P is very high or very low, right? The P is middle is the highest, okay? That is the thing, okay? And now I guess the most useful one is not that one, but the general case is you have n independent binomial trial, right? Just the 0 1 thing, but you repeat doing that, okay? And you are saying that I just run this trial n times independently. I count how many success I have, okay? And this one actually gives you a bell, or sometimes we may call it discrete bell, okay? And the way this probability, I mean, the thing is you have to remember this formula, where to get this formula. You don't have to, at least you know this formula comes from. But of course, later when Excel, it's already there, okay? But you just know how Excel gives you this number, right? And this number is not very hard. You have X success, okay? Which means that suppose you want to have first X time is actual success, right? Suppose N is 10, X is 3, right? So how do you get 3 success? To get the first 3 times you're successful, the rest of 7 you get fail, right? So it's P times X times this guy, right? But this is one way of you obtain 3 success, right? You can have 7 failure, then followed by 3 success, right? And or you can have first 4 failure, 3 success, and 3 failure, right? And there are many ways to do it. And how to do it is NCX, okay? Why is the case? Because you can imagine this n balls, right? And each ball represent the success at the nth trial, ith trial, the ith ball. Then you're just asking you how many ways you can draw x ball out of n, right? But if you don't understand the logic, doesn't really matter, okay? This is the formula, and you'll be used, okay, to do calculation, okay? And I have to remind you that there are things that we don't explain, so we just skip the formula sometime. I try to explain, but not easy to understand. I'm pretty sure not everyone able to understand. Because when I learned it, it took me like, I don't know, maybe 1 or 2 years to fully understand this. Maybe I'm not smart enough, but I think my classmates, they all understand. But it took me quite a while to fully understand why this formula is correct. But I think if you try to draw a tree diagram, may be helpful. But if not, then it's okay. Just remember the formula, and sooner or later you understand. I guess the most easy way to think is a blind marriage. Okay, you marry with that partner, the spouse, and sooner and sooner, after year by year, you understand what's going on. Okay, same as this. You have to use it. That is the formula, and one way or the other, you will get it. Okay, and the idea of this is once you have that formula, the thing we need is the mean and variance as well. Okay, beside that probability, mean and variance is the thing we would care, because we want to care about mean success or the variance successful. Okay, and I'll try to give application in a few slides after. Okay, and so just one of the application in your slide as well, right, is talking about food preparation. Okay, if you're a restaurant owner, okay, you sell spicy food and non-spicy food, right? And look at the historical data, 30% of the customer like spicy food. Okay, and what is the business problem here is if you are the restaurant owner, you need to prepare spicy food before they come, right? The spicy food cannot be prepared on the fly. You have to put it in the spicy sauce sit them there for a few hours, right? The question is how much spicy food you need to prepare, right? It depends on how many customers actually order spicy food. So the question is, suppose, right, the restaurant is very small, make it simple, only have five seats, right? You can change this number whatever you like, but the idea is the same. Asking exactly 2 of them like spicy food, right? Of course, you can calculate exactly 1, exactly 0, which will be done in the next slide, but calculating exactly 2 first, okay? And this is very simple, right? Because every one customer is a random draw, right? Why this is the case is imagine these customers are not related. They're not in the same family, then they're independent, okay? then it's good to use this idea. Assume this is a binomial, n is 5, x is 2, and p is 0.3. Okay, you can imagine that a customer is rolling a die, right? A die just rolling a die, and this die come in. Okay, this is okay. The light spice or not, right? Or toss a coin, right? The coin, right? If one side comes in, spicy food, otherwise not, right? And the same idea. Then this is a good model. Okay, and why this is good? Why this is useful? Because of I can use it to calculate what's probability that less than or equal to 2 people, right? And without going into detail, go to the solution first. It's 84%, right? What does that mean? It means that if you're a restaurant owner, maybe you only need to prepare 2 portion, right? Be enough, right? Portion for 2 customers be enough, right? Because that would be the thing, right? So how to do calculation, right? You multiply, right? And you calculate all of them, right? That will be enough. And indeed, if you do the mean, what's the mean? N is 5, P is 0.3, mean is N times P is 1.5, right? So if you just care about the mean by itself, only average 1.5 people is going to be there. Okay, of course, you can calculate variance as well. But to be safe, you look at this, 84% is sufficient for our purpose, right? So maybe 16% there's some customer are not satisfied, right? So you can make decision, right? How to do this in a more elaborate one will require you to study further, right? Later you study marketing, inventory management, they will tell you more stuff, but this is the basis of how you, as a business, make decision. Okay, it's not by guessing. There's a probability to help tell you. You can tell your manager or your owner. You can tell how much stock you have to prepare. Is that clear what we are doing? Okay. Just to remind you that this is one of the milestones of this class is probability modeling, right? Use probability to come up with that, right? How do you get 30%? Come up with historical data. Okay. And how you get 5 customer depend on size, right? Also from the later you can guess how many customers you come, right? Also you can do those, right? And here is I add this line last slide. Doesn't really have, I mean, nothing new there, just some description, not particularly important, and I give some example because yesterday some of your classmates from other section actually suggest me I should give more example to give you more little bit taste of this because this is so important, so I just put it there, right? So imagine a marketing campaign, right? Later I'll give numerical example detail, but this is the thing you would do, right? My campaign, you can calculate how successful is your campaign is by looking at the outcome. And say quality control, you want to see how likely that you are going to find out a defective product, or you want to calculate as an HR, calculate probability of turnover, and you can guess how many people you need to hire, right? And you want to calculate reliability of your software, and also the inventory management we just saw, right? The spicy food case is actually inventory management. Okay. Now I quickly go into some example there. Okay. Imagine this example is a company do a marketing product, it target 10,000 people, and you imagine that 5% of people would do it. Okay. How do you get this number? Historical data, right? Or come from marketing guide to tell you. And then you can use binomial. You assume customer are independent, which might or might not be reasonable, but you have to make some assumption, okay, to start. And you can calculate exactly 500 will be this probability, right? And you can calculate 500 or less, right? You can calculate any number because you can calculate this is 500, you can calculate any number. And then you can evaluate, okay, how successful is your campaign is, right? If because why 500? 500 is the mean, right? And actually can calculate what are the numbers that, and then you can evaluate how successful you are, right? At the end, if you do this, if like only 300 people comes in, you can evaluate how successful that you are. Okay, but of course, the further of doing this is beyond the scope of a class because we are not doing particular marketing, right? The same idea, right? You can look at quality control, right? And then you want to see whether the defect rate is going to be correct. How you do, right? You collect 100 sample, and the quality control people tells you the machine is good for 98%, right? So 2% a problem, right? And then as a CEO or the operation manager, you want to check if the number is actually correct, right? You just go there and test, right? And you figure out that actually you figure out maybe 5 of them actually defective, and you calculate how likely they are, right? And then of course you can calculate a lot of probability as well, but this will help you to do the job. Okay. And similarly, you can do the same. Look at turnover rates. Okay. And you can decide based on this how many employees you need to hire, right? And I'm not going into the detail for this one, right? Same, you can see it's a good for a binomial and distribution as a model, right? And similarly, you have quality assurance. Okay, and you can take this, but I guess it shouldn't be an issue for you. Is that clear why I need binomial? Right, because as long as you assume there are some rates from historical data, and you have many sample, and then you can check, and this is you just apply directly. Okay. Maybe in the meantime, I guess it's time for break. I open and you reply, and then you can give me the feedback. If you don't know, you want me to discuss more. Okay. So let me open and you reply. Let's have a break. We'll resume at 2:32. Or 33, sorry. I open the you reply. So time, please fill in, and then so that I know whether I'm going too fast or going too slow, or you need some more application. Because last class, I mean, you reply, some of the students actually tell me I'm going too fast, so today I slow a little bit and give you more application. You can let me know whether you like it or not. But go to washroom and come back. It's about time. Then let us see the result. The first question is why you want the variance to be small? Because you want to minimize your thing in portfolio, right? Suppose X is the bond portfolio, X is stock X, and you have two investment X and Y, right? How you choose two investment, right? Is you want to make the risk of investment as less as possible. Of course, you want to maximize your expected value, right? But you also want, at the same time, want to minimize that, right? This is classical ideas, risk and return, right? And the main idea is that, let me go to the slide, right? This is an advanced thing, but I think it's good to talk about because this is one of the application, right? It's the finance about mean and return, right? Is you want to choose how you choose two different stocks, suppose the simplest case, right? The idea is you want to choose the one that has good mean, but the variance is not very large, right? How you make sure not very large, try to figure out things that is not related, right? Just like the simplest idea, right? You put that you have 2x, you want to save it for tomorrow, where you put those, right? You want to put one egg in one table, the other in the other table, make it safe. Or suppose you want to build a factory or do a business, right? You want to put the same restaurant in the same area, or you want to put the restaurant in two different areas so that they kind of isolated, right? Because put in the same area, they can do both well. If they do badly, they do badly, right? Then the variance is much larger instead of putting two different areas, right? So that's the idea. I hope I answered your question. But don't worry, it's not in our syllabus. I just mentioned because of that is something that I feel is the most useful. Slide 54. I'm not sure my slide same as your slide. I guess this one is right. Is it this one I want to explain? Is it what is up? Slide 54. Yeah. Oh, okay, this one. Okay. So someone asked me to explain this again. Oh, sorry. Explain this slide again. Okay. So what is binomial distribution? It's actually you are repeating the binomial trial. What binomial trial is? Each time the random variable is either 0 or 1, either success or failure. Right? That example is the first customer. Is it going to like spicy or not spicy? And the probability is 0.3 in the example. Look at the second guy. Suppose the second guy is independent of first guy. Ask him is whether spicy or not spicy. And go on until go to the last one. Go to the 5th guy, right? And count how many people actually spicy. And how to calculate this probability, suppose, will be by this formula. And this formula, if you understand that, not that's fine, but I try to explain. It's saying that if you want to have, say X is, N is 5, right? X is, say, 2 of people like spicy, right? How you do it is the first 2 people like spicy food, and the rest of people don't like spicy food. This one way to it happening. But also you can have the first 3 doesn't like spicy food, the last 2 like spicy food. Or it can be the second guy and the 3rd guy like spicy food, right? How to count those? How that is 5C2. If you don't get it, you can just draw a probability tree that will get you the same answer. But this is the formula is being used, and this is the exact formula to get the probability. And the mean and the variance also very useful as the way that you do decision. Okay, I hope I answered that. If it's still not clear, hope that you can ask me at the end. We want more supplementary exercise, not homework. Yeah, we look at my lecture notes. It actually contain exercise. So you go to here. There's a notes here. You can go inside. I think I wrote this book, and the importance of this book is to give you more information, but you can look at the exercise. Exercise also contains solution. You can just click them. You can click them. Then I think they give you the answer how I do those. These exercises are given as a past quiz when I taught this in the first 2 years. But I decided quiz is like not very useful use of class time, so I give it up. If you want, I can take it back but I guess that's not really helpful. But then we can do it at home if you want to. Of course, any textbook would work because we are introductory class, so you can easily find one. Okay, and if you still want, let me know. I mean, we can figure out how to do more. Okay. When we use binomial distribution, as we said, you imagine that the process is like the first guy follows some probability, yes and no. The second guy also the same, and if they're independent, then that's it. Okay, that is count how many people say yes, successful. That's when we use it. Okay, and then we give an example already, right? So in the case, the example would be like the spicy food idea, right? The marketing campaign, all these actually follow binomial. Okay, and of course you will use it in the future, or the business decision that involve understand the future. Actually, a lot of time binomial is the way to go, right? Because it's success or failure, right? Count how many of them, right? If you're able to tell how things happen to one guy and this apply to everyone, then it's a binomial. All right. I hope I answer your question. It is too fast. Yeah. It is not easy to understand, I'm pretty sure. Because if it's the first time for you to learn, this is difficult. But the object is very simple. You just imagine the toss a coin, right? Imagine every guy, every observation toss a coin, right? Do you have a guy? Does he like spicy food? Toss a coin. The coin decide whether he like it or not. You have to imagine that the future is like tossing a coin, right? You have four customer, 5 customer. Each customer is whether he likes spicy food, toss a coin. And the example we have is like, right? Marketing campaign. You have 1,000 of customer, and each customer whether he would buy after seeing your ad is like 5%. Toss a coin, and count how many of them actually buy your product. Is tossing 10,000 times a coin. Okay, I think tossing a coin is very easy to think. If you think each one realizes following a coin, then how many of them actually count the total coin outcome is the thing is use binomial. I hope now it's more clear, but I'm pretty sure the first time you learn it's not easy because this is involved what we call probability modeling, right? Use probability to describe the thing that you want to discuss is something not easy. Yes, that is not easy. But this is one of the application for this class, right? Applying probability to describe the future, to do business decision. Okay, of course, we are unable to give further because in order to do further, we need a little bit more stuff, but at least it's starting point, right? Because you want to do decision, you need to do cost and benefit analysis, right? What is benefit of doing this and doing that? That require more tools, but this is the starting point. Okay. I hope this is more clear. But if still a question, welcome to ask me this class or next class. When you do assignment, you will be no more. Maybe I will release assignment earlier in order to see what are the possible questions. Again, assignment you're given 2 weeks to do. After you end with the first assignment, with 2 more weeks. Although I release earlier, doesn't mean you need to do earlier. But I just reduce the anxiety you worry about what kind of assignment you will see. Okay, I will release earlier. Okay, so that you know what's going on there. Okay. So just make sure you know today is Thursday. Okay. Yeah. I think the day is windy is fine. So Yeah, binomial, that's good. So everyone, I think, has got it. So I agree that today's lecture is not that easy. Okay, I'm pretty sure but we'll be doing the same style of stuff. The rest will do Poisson and also hypergeometric. And next week we will do exponential normal. Then you will see the same thing happen. We just learn a new type of structure, mathematical structure, distribution, and then we learn how to apply those. Okay, and it's not that easy for sure. For most of you who haven't learned it, okay. I love you hand sign. Do I do that? No. I try to explain slowly. Let me know which part you need me to explain more. I will try to be slower. Okay. Thanks. I should be slower. I don't know. I haven't released the grade yet, so I don't know what free stream combined mix. Ha ha ha. Supposed to be a joke. Okay, that's fine. So I take your advice. I try to be slowed down a little bit. So I give Poisson, then hopefully this one will be the easier. Okay. So Poisson is, if you understand binomial, Poisson will be the same thing. Okay, but just the idea is slightly different. Okay. The idea is following. Maybe I draw a picture to help you to understand this. Where's the pen? Oh, here. Okay. So maybe I give idea of okay. Remember, binomial is what? Binomial is we have asking the following, right? We have 1, 2, 3, right? Up to n, right? If n possible cases, right? Each time you toss a coin, head or tail or success or failure, right? Or we call success or failure, right? We call it P1 minus P, right? That's the idea, right? We go to the first box and try to see is head or tail or success or failure. Each time success have probably P, failure 1 minus P, right? This is a binomial, right? And I think this applies to many, many cases, right? As long as you think that each box, the opening of each box is independent, then this thing will apply. And this applies to, I think, most of scenario, if you consider future is either success or failure, right? You can consider this is like P is the probability that the typhoon will hit Hong Kong, right? And as long as you make this box are big enough, then they're independent, right? Because if you make it every day, then probably today we have typhoon and the typhoon next day will be independent. But if you make it like each box is as large as a week, then I think that should be fine, right? Each week the temperature or weather should be independent, right? Should be fine. So how you apply this, it really depends on application, but I hope this become a little bit clear. Okay, it's what we mean by binomial. Okay, I hope there's another way to see what is binomial. So you can see here, I have n box, right? Each box have either success or failure, and Poisson is very simple. We just have n very, 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 very big, and that's it. Let me repeat. Poisson is simply the binomial when the n is very, 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 very big. Okay? And you ask why I need very, 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 very big and what's the use of it? Okay? So very simple. The idea is the following. Okay? It's the idea of time. Okay? It's modeling number of people arriving. Okay? This is the time, suppose this is a from 0 to 60 minutes or 1 hour, right? 60 minutes. This is 1 hour, right? 1 hour. Okay. You can cut 1 hour into 60 minutes, right? And you can even cut 60 minutes, each minute you can also cut into 60 seconds, right? And then each box, each interval, each small box is just 1 second, right? And what do I do that? Because I want to model this as how many customers, say, arrive in that second. I cut it so small, only one person can arrive in each second. Why do I do that? Because I can model it as how many people would come in this hour as a modeling of arrival. Okay? Arrival, how many people would come? How many accidents would come? How this is the arrival, right? Is how many things can happen within a time period is the Poisson idea, right? The idea is to cut the time period into very small interval, right? So small that only one or zero would happen in this interval. Then we can apply the idea of binomial, right? Because you just each second you just see open the box, accident happen or not, and the second minute go or not. You can count within that time period how many things can happen. Okay, before the binomial have no time, right? But a lot of time we talk about time, where each day how many customer is coming, right? This is the application. Is that clear what we are doing? I try to be slower, but because we're not in a hurry anyway, so it's important to understand rather than go over a lot of subjects, right? Is that okay? If it's too slow, let me know. Okay, I try to be slower, but I will give more example. Hopefully that would be helpful. So without looking at the math, right? So it will be just this, and we don't do any proof. Okay, just the proof will say if n is very big, it will become this guy. Okay, this is the math. We don't prove at all, and the only thing that something that is in your mind is what's the E here. Okay, E is just a number called natural number is 2.713. But anyway, we just consider E is 2.713. Just a number there, nothing new. This number raised to the power NP. Okay? So that is it. Okay. And as I said, the usage is customer arrival. Okay. And very often we model this, right? In this time period, how many things happen? Right? Is that okay? Customer arrival, right? This is the main thing, or demand, right? Is that okay? What it is? Okay. But do note that there is an important assumption for this to work, and that is the reason why you need to study further in the statistics class. Is the important is independent, right? The idea is being that go to the box idea. As I said, you open the box here, what's the outcome in the first box has no bearing on the second one, right? But you can imagine that for application of restaurant, say, right? If there are some customer coming there, people saw your restaurant has a lot of customer, they tend to come in as well, right? So it's not independent in some cases, right? And often for a restaurant, there's a peak hour and off-peak hour. During lunchtime, you have more customer, and tea time is less customer. So you have to separate your modeling into lunchtime, non-lunchtime, right? For hospital, for hotel, you have peak season and non-peak season, so on and so forth, right? So that would be the thing you need to look after when you actually apply it in the practice. And but of course, those things would require a lot of skills that will be reserved usually for 1,000 classes. Like you go to stat department, they learn stochastic process, or I think 4,000 in our department also talk about those. But this is not a concern. We assume, okay, this is the same in the whole period. Each thing is independent, okay, because same as binomial. So everything will apply. Okay, let's go back. Don't worry, we will give example for that. Okay. So there are several things goes on here. One thing is because we say n is very large. Okay. So what the random variable can be is go from 0 to infinity. So 1, 0, 1, 2, 3, 4, 5. There's no limit. Right? There's no limit, unlike the binomial. Okay, because binomial we have n box. The maximum we have is just n. Here there's no upper limit. Okay, but of course it's only in theory, not important. And usually we will call NP because you look at the formula here. NP just appear once together, right? NP always appear at the same time. So we instead of calling NP, we will call lambda. Okay, as you may expect, lambda with the mean, right? Because this directly coming from binomial distribution, right? Binomial, that means NP, right? And now NP is lambda, so this is exactly, there's nothing new there. The only thing new there is the variance, okay? And now it's surprising, variance same as the mean, which is not the case in binomial. You ask why? Because binomial, in the case is like this, NP times 1 minus P, right? But do remember what is the Poisson here is I cut the time interval so small, right? That each interval is so small, right? The P is also very small, right? Because every 1 millisecond, the customer coming is very little, right? So that's why P is close to 0. So this guy is gone, right? This is lambda. Is that clear why this is the case? Of course, you can actually prove it, but that is the idea. Okay, and we don't really need anything special, but you can notice the interesting thing, the mean and the variance are the same. So this is a very particular interesting case for Poisson. Okay, and of course, those of you who maybe think I'm going too fast, the only thing you need to remember is Poisson is to measure how many people in a period of time, and this is the formula. And this is the result. And when you apply is you assume things happen in the first hour is independent, things happen in the second hour. You think that apply, they will apply. Okay. And let's see the example. I think hopefully that will give you an idea. So additionally, this is the PX graph. Okay. And you will notice when lambda is not very large, that will look like a asymmetric, right? Positively skewed one. But when lambda is slightly larger, it becomes a little bit bell. And indeed, your idea is correct. If lambda is big enough, same as binomial, it will be a bell shape. So you can use normal distribution when you learn the continuous version. So everything actually turned out to be bell shape, luckily. So that's why after this topic, we will basically everything is bell, very normal bell. But before that, we will keep this thing. Okay. Now, let us give an example. I hope I go slower. Will motivate why we use Poisson. Okay. And the question here is, I have to estimate how many customers would arrive in the next hour. Why I want to do that? Because I need to decide as a owner how many employees I need, how many food I need to prepare, and so on and so forth. Operational concern. Okay. The idea is I look at the customer that arrive in a restaurant each hour followed by Poisson of 5. And the Poisson, why Poisson? We just do the assumption. Okay, it's given by the question, and I explain when Poisson is a good one. Okay, and that is, I mean, and I guess for your purpose, as a first time you learn, Poisson is fine. Okay, and then there's a lot of paper actually, I mean, a lot of application actually just Poisson. Okay, and the question was asking is like, say, what is the probability 2 customers coming? Right? So the idea is not difficult, right? So we just apply the formula, right? The formula is like this, right? If you remember, or you check out, don't worry. Formula, you can always bring it to exam, okay? And you do assignment, go check, right? So you don't need to worry about the formula is complicated. It's not required to remember. Right? The formula is like that, right? And later we will learn Excel. Excel will tell you directly the answer, right? So there's nothing you need to worry about, even calculation. You need to know which Excel formula to plug in, and you're done, right? So, but you need to know how you get it, right? Otherwise, you don't even know what the computer gives you correct or not, right? Because these days, you can use AI very easily, right? But AI often not smart enough that you have to decide ultimately whether it's correct or not, right? Because sometimes they hallucinate, right? They give you something seems to be sensible, so to check, right? But the idea is very simple, right? Just put lambda is 5, x is 2. Is that okay? Because that will tell us the probability exactly 2 customers arrive. And okay. And in the practice, you'll be same as the previous example. You want to calculate the probability that actually 2 or less people arrive, right? Then in that case, you can decide how many food you want to prepare, how many staff you need to hire, how many tables you should put in the restaurant, so on and so forth, right? Or you can calculate probably less than 3, or so on and so forth. There are many calculations you can do, right? Because by knowing this, you can calculate every probability, right? Exactly 2 is 2, right? Exactly 3 can calculate 4, 5, 6, right? Then you can know how the bell look like, and then you can decide what to do. Is that clear what we're doing? Okay. So let's give example as someone tell me I need to slow down. Okay. Let's go to the example. I hope that would give you more idea. Okay. So let's quickly go to some example here. Okay. Example is the call center. Okay. And you would like to see, because the call center within the office hour, you want to see how many call comes in, then that will decide how many staff you need to put in. Okay, let me see the example, and then this will go one by one. At least 3 of them and see, right? The example like this, okay? And look at historical data. The call center on average, you have 50 calls per hour, right? And you can use Poisson, that's what we do, to calculate, okay, how likely you have more than 60, okay? And then you can calculate how many staff you want to do, how to calculate the waiting time, how to do resource allocation, okay? And because if you assume Poisson, okay, then the formula is like this, right? E to the lambda x and x factorial, right? And this is the formula, right? You can calculate 50, right? You can calculate any number, right? 60, 60, 61, 62, 59, then you can all actually go to Excel spreadsheet and do everything very quickly. But this is the idea behind, then you can calculate a lot of situation, right? Let me give another example. I hope this convinces you it's very useful, right? And consider website traffic, right? You want to see how many people actually visit your website, right? Especially Netflix or other, they use a lot of bandwidth, right? And you need to buy to make sure that your server doesn't go down, right? And that happens, right? So an example like this is like this, right? Suppose a website, they have 500 people visitor, right? And you want to calculate that probability that is 600. Why you care about that? Because if you are a lot, then maybe the server breaks down, the customer have to wait. You need to make sure that how many, suppose how many bandwidth you want to buy, right? Maybe up until certain number, right? You calculate what's probably that for that or above, right? If small enough, then you're fine, right? But of course, how to make this kind of decision it will be another class, okay? But this will tell you how to calculate those probability. And another class will tell you, based on this probability, how you make cost and benefit analysis, okay? Cost and benefit analysis is beyond our class. I cannot tell you, or we can just learn how to calculate probability, okay? So that's why you may feel difficult, because we don't go to that point that become less concrete. but at least we know how to calculate this probability. And one step further will be other class. So I understand difficult because we don't actually go to that spot. But you can easily see how you go to that spot, right? If you specify what's the loss, if you do that, what's the gain of doing that, then you can do those. Okay. So you can assume Poisson, then this is very direct, right? Because lambda is 500, x is 600, this calculation, right? You can just vary, right? Calculate 600 or more, right? That's the idea. So this is already in the blackboard, so you can just download the new one. But I just add the new examples, okay? And probably one thing that would worth talk about the Poisson is, remember, this worth talk about is this is go to infinity. Okay. So here that means that you need to use complement rule sometime, because when you calculate more than whatever, you can calculate what's less than that, you can count. Okay. So that complement rule will be needed. But don't worry, you will see this from, I think you will see from our classwork or exercise. Okay. And I'm not going to detail, but you can see calculate how many defective product within certain time. Okay. Then maybe you need to calculate how many truck you need to get to trash them, right? Service downtime, and how many insurance claim will be made within a period of time, right? Or the bank that is actually they do, right? How many people will liquidate that deposit, right? Then to see how many cash to put in the banks, right? So these are the problems, right? That actually is very useful, right? Because remember, all this is asking is within a period of time, how many of those things you need, you have, right? And whether you have those is probability, right? So it's very common, right? Within a time, what things will happen or not. Is that clear? I hope that will be clear, right? Because in the binomial, you're just asking if you have n thing, right? How many of them will actually success or failure, right? We have n is the number, right? But here is just an n is a time dimension. Is that clear? Okay. Okay. If it's not clear, doesn't matter. To next class we will do review. I'm not going to end one by one because I want to end today's lecture with another one. Okay. Don't worry. This is actually also very similar to binomial. Okay. And application-wise, it's also very similar. The only difference between binomial and this what we call hypergeometric, sorry, just scare me a little bit. Hypergeometric. Okay, the reason why the name is complicated because there's something called geometric, and this is the hypergeometric. But the idea is very simple. Binomial, remember, is what? Binomial is I go to each box is success or failure, right? So each box is independent, okay? But sometimes not the case. Imagine that the following is the situation, okay? The easiest to understand is imagine you're doing audit, okay? You go to a warehouse. Warehouse, suppose you have big N, you have 100 items, okay? And the client tells you 30 objects are good, okay? They said 30 of them are good because A is 30, they're good. So you have smiley for this 30, okay? And that means that n minus A is 70. 70 of them are bad. Okay. Your job as an auditor, try to verify his claim. Okay. You already came. How do you do that? Of course, you can go to check 100, then you're done. Okay. But of course, if you do that, you get fired because you never get it done, right? So how did you actually do it? You would do it by what we call sampling, right? You just pick up some and then see how many of them are good or bad, right? Then what you're going to do, the question is you would be doing something here. Get something here. We call small n. It's the size of the sample, okay? And we're asking how many probability of how many x of them among that x of them is happy, and n minus x is not happy. Okay. We're asking the probability of x. Okay, so that is the question. Okay, now let me give you, this is the idea. Okay, just basically just like I pick out 10, say n is 10, right? I take say about 10 objects, right? Okay, I take out 10 objects, and if I do it as an audit, I figure out 3 of them are bad. Okay, 7 of them is good. Okay, then you will say, okay, that looks like good because the proportion is similar to this one, right? So you may be okay, right? Because they said 30% is bad. You figure out 30%, right? Then probably that will be fine, right? But if your data is like your x is like 7, okay, then how are you going to conclude? Okay, of course, the way to do it is just calculate this probability, right? You take 10 items, given the claim from the client, 7 of them is defective. If the probability is very small, then you would be, hey, come on, you must not be telling the truth, right? That's the idea. Okay, and that is actually what we call, in the context of sampling, this is called sampling without replacement, because you do things once and for all, right? You take it out, you don't put it back, right? You one take out and take, right? Sampling without replacement. If you model, you can also model this as a binomial, right? Probability of each one success is 30%. But in that case, you're actually doing sampling with replacement. You take one thing out, you put it back. So every time it's 30%. And you ask which one to use, depend whether you actually put back things, right? If things are, each row is dependent, right? Then you will be the case, okay? And you will see that if this n is super big, doesn't really matter for binomial or hypergeometric. But you will do this as an auditor. If you go to check, this is, you can decide how many to check, okay? And if you actually decide how many to check in the, how this n and the rule, whether you will jump up to your client, of course, that will be something come from other classes. I just tell you that how to calculate this probability and how to use this probability to arrive your conclusion is not our class will include, because it involves more things to study. But we will tell you how likely you get this. Okay. So let me give you an example. Okay. Is that clear what we are doing? Okay. It's just you are imagine you are not opening an n box, but you are given this scenario. Okay. And that is the idea. Okay. Anyway, this is actually you have more details on the thing, right? How you do things. So that is slightly different. It's called hypergeometric. And okay, the formula is not complicated, but of course, I'm pretty sure that not everyone got it at first chance. But I give you some idea why the denominator n, big N choose n, because you have n object choose n, right? That's how many things you do. And how many things you can do, you have x 7, right? So you 30 good stuff, you want to pick 7, right? And you have 70, you want to pick 3, okay? Because it's principle of multiplication, right? Because you have to choose out of all the good things, you choose the thing that, right, is there. And this is the thing that go there. Okay, but don't worry about the formula. This is, if you don't get it, it's normal. Okay, as I told you, I don't get it when I was a student the first time I learned it. So if you do it, you learn it, because if you actually need it, you need it later as well. So you understand. Okay. So the mean and the variance look like this. Okay. I don't want to overemphasize this, but when n is 1, a over n is just p, right? Or this is p. Actually, this look like the mean same as binomial, right? And if a over n is p, this is 1 minus p. And when n is very big, big n is very big, this guy goes to 1. So this is same as binomial. Okay, but anyway, I'm not expecting you to remember all this. Okay, the main thing is look at this example in the warehouse. I guess this is I talk about this and we end. Just 1 minute. Okay, so this warehouse, I have, as an example, I have 30 computers and 4 of them are defective. Okay, and that basically tells us this, right? At the warehouse, n is 30, right? And a is 4. Okay, because I only care about defective. A is the thing we care. Okay, and the question is 2 out of 6 is defective as well, and is 6 given from this, and this is x is 2, right? Out of 6 of them, 2 is defective, and this is the probability. Okay, and how to use it further is other class. I cannot tell because you need to say what is trustable or not trustable. What is probability you will jump up, but you will complain to your client. But this is the idea. Okay, I guess it's right time. So I will see you next Monday. Okay, and I'm pretty sure that you may have some problem that you can look at the textbook, and I also release assignment for the next one so that you can have less answers about what is asking. Okay, but the assignment 2 is not formally released until the assignment 1 is done. Okay? So you always have 2 weeks to finish all of it. Okay, but you have some idea what's going on. Okay, I will see you next week.